Hello and welcome to the course of Advanced Algorithm Analysis. In week number 12, we studied about graph theory, terminologies and concepts related to the graph, and also some basic searching techniques for searching for a node in a graph. The technique that we studied were a breadth first search algorithm and depth search first algorithm. In this lecture, we are going to study another very interesting and important topic, which is known as the greedy approach. The roadmap for today's presentation, as usual, we will start with objectives of the lecture, what you are supposed to learn at the end of this lecture. After briefly describing the objectives, we will shift our attention to the optimization problem and then the approach which is used to deal with it, that is the greedy approach. Then we will describe the concept which is known as spanning tree and minimum spanning or cost tree, and then two algorithms for finding the minimum spanning tree, that is Kruskal algorithm and Prim's algorithm. This is the brief agenda for today's lecture. The objectives, as I just mentioned, at the end of this lecture, you would be able to understand the concept of a greedy approach, and also you will learn about minimum spanning tree and two algorithms for finding the minimum spanning tree, that is the Kruskal and Prim algorithms. Before going to start the concept of minimum spanning tree, let me introduce what is an optimized problem. In the field of algorithm analysis, some problems can have many possible or you can say feasible solutions. And with each solution having a specific cost related with it. And being an analyst, we always wish to find the best solution having the optimal cost. For that, we are always interested in finding the optimal and the best solution among the available possible solutions. So you can say that a set of choices must be made in order to arrive at an optimal solution. The optimal solution in some cases it could be the minimum possible value, or in other cases it could be the maximum possible value of a problem subject to some constraints. For optimization problem, we actually have two common techniques available. The first technique is known as greedy, and the second is known as the dynamic programming. The focus of this lecture is greedy algorithm, but we will also shed some light on the dynamic programming concept. So let us start with the greedy approach or greedy algorithms. Actually, greedy algorithms sometimes they work very well for optimization problems, and they are easier to understand and easier to code or implement as well. And this approach is frequently used in our everyday problem solvings. Let's suppose you are choosing a job and then you are going to make your final decision. That decision could be based on the greedy approach. Or you are traveling to another city or another destination and you are going to find the most suitable route for yourself depending on several factors, or as I just mentioned, constraint like the traffic conditions on the road, the weather, the condition of the road itself, the time required to reach to the destination, and factors like that influence our decision. In a similar way, if you are playing the cards game, playing cards, and then you want to place a card. Certainly, you have different options, choices available. Now, how you will make your decision, it could be based on the greedy approach. Or if you are investing in the stock where you will invest your money to earn more profit, could be based on the greedy approach. So a greedy algorithm actually works in different phases. And at each phase of the greedy algorithm, we makes the best choice available, but at the moment, right now. That is the property of the greedy algorithm. We always want to make the best choice in the current situation, current circumstances, without regard for future consequences. And then we hope to end up at a global optimum solution by choosing a local optimum solution at each step. Okay, so in summary, in the greedy approach, we always try our best to make the best choice available right now in the current circumstances without regard for the future consequence. We will come back to the greedy approach in a moment, and we will study in more details about this. But first, let us see what is actually the dynamic programming approach. As I just mentioned, we have two different techniques available for optimization problem. The first one is greedy algorithm, which is going to be the focus of this presentation, and the second approach is known as dynamic programming. Dynamic dynamic programming concept was introduced in 1950s by Richard Bellman. It is actually mostly in most cases this technique is applied to optimization problem like the greedy approach problem. Okay, let me tell you one thing, that the dynamic programming actually it doesn't refer to computer programming, but it is a strategy for designing algorithms. And to be more technical, it is actually a meta technique, not an algorithm that we use, that we follow to find the optimum solution to a problem. Okay? Programming actually solves every sub problem just once. We make a choice at every step towards the solution, and our choice depend on solutions to sub problems. And in dynamic programming, the approach that we actually use is a bottom-up solution approach, or you can say we are moving from smaller to larger sub-problems. Uh, you might be thinking or comparing the dynamic approach with that of the divide and conquer approach. Because in the divide and conquer approach, as we saw in case of merge sort, quick sort, binary search, it also solves problems by combining solution the problems. In order to elaborate further the divide and conquer approach, we partition the problem into independent subproblems, and then we solve the subproblem recursively. And finally, we combine their solution to solve the original problem. Same is the case with dynamic programming. However, dynamic programming is applicable when the subproblems are not independent. Sub-solutions are the solution to the subproblems, or the subproblem itself, they are dependent on one another. Beside from this difference, we also have another difference between the divide and conquer approach and the dynamic programming approach, and that is that the divide and conquer approach is actually a top-down approach, while on the other side, the dynamic programming is a bottom-up approach. Okay? Let us bake our attention to the greedy algorithms. I'm supposed that you are familiar with the word greedy. If not, let me elaborate it by using a reference to a study that was conducted by the researchers in the University of Oxford, and the study was published in Natural Communication. And the study brings out an interesting fact, and the fact was very simple, and it proves that greedy is something which is good. According to that study, in the hierarchical structured communities, the class at the top of the community, in the community, it actually takes care of the lowest in the hierarchy, and they also compete with the classes at the top of other groups. Actually, we see some greediness here, and greediness is good for those that are superior in their groups, and also for those that are at the lowest level in that group. You can also find several examples of this approach in our society. Even in our religion, it has been said that you can compete with your fellows while learning something that is allowed. That type of greediness is allowed. Even our economies run on the basis of this greedy approach. And also the companies, they are able to survive because of this greedy approach. Everybody wants to select the best approach towards the solution. Even those who rule us follow this greedy approach. So up to some extent the greediness is good, and the rule also apply on algorithms. The problem solving approach that incorporate, you can say, a pinch of greediness, it actually helps us to attain the goals in a better way and perhaps in less amount of time. So this greedy approach of solving a problem calls for the selection of most promising intermediate solution at that particular time or at that instance of time. The intermediate solution, which seems promising at a point, might not be good in long terms. Remember, in the greedy approach, we always try to select the best solution at that time or at that particular instance of time. But maybe in long terms, our solution is not good. In order to solve a problem with greedy approach, we actually select an input, and if the solution satisfy the greedy goal that we have set for it, then it is taken in the solution set. Otherwise, it is left. So we have some goals in our mind, and then we select a problem. And to solve that problem by this greedy approach, we select an input. If the solution satisfy our goals, the greedy goals, then it is taken in the solution set. Otherwise, it is left. Okay, so in conclusion, the greedy algorithms work most of the time. However, they are not always optimal because we always consider the solution that are best at that particular instance of time. Let us move our attention to the spanning tree concept. A spanning tree is a subset of a graph. For example, the graph is denoted by G. So spanning tree is actually a subset of a graph. However, it must satisfy some properties. What are those? The spanning tree, in a spanning tree, all the vertices are covered with minimum possible number of edges. That is the basic property of a spanning tree. Means the first point is that it is actually a subset of a graph. Second thing, all the vertices of this subset of graph, they must be covered, mean they must be connected with minimum possible number of edges. Okay? If we are interested in finding the optimal solution, in this case the optimal solution is to reach to the destination with minimum possible number of edges, or you can say the cost, minimum cost. Another thing which is important for a spanning tree is that a spanning tree does not have any cycle. This is something very important. Cycle, the concept of cycle we have already studied in the graph terminologies. Starting and ending point is same, which means it is a loop or a cycle. So in case of uh, a spanning tree will not contain any cycle. And another thing is that it cannot be disconnected. Like a forest where one or more than one nodes are not connected to the rest of the of the nodes, or to the rest of the graph, subgraph. So all the vertices must be connected, must be reachable. And by this definition and from these properties, we can draw a conclusion. And the conclusion is that every connected and undirected graph has at least one spanning tree because they are connected with one another and there is a path from source to destination. So the conclusion is that every connected, only connected, not the, the definition will not be applicable on the unconnected or not connected graph. And also the graph should be undirected. So if a graph is undirected and it is fully connected, then you can say that there exists at least one spanning tree. At least mean it could be one, it could be two, it could be three, and so on. Okay, I talked about connected graph. Now, what about disconnected? A disconnected graph does not have any spanning tree because it cannot be spanned to all 8 vertices. Remember, it must be connected. So if a graph is disconnected, then uh, it cannot contain any spanning tree. Let us see some general properties of a spanning tree. We now understand that a graph which is a connected and undirected can have more than one spanning tree. So it leads to some properties, and these properties are for connected graph, undirected. The first property is that a connected graph can have more than one spanning tree, and we just saw it. It is possible for a connected graph to have at least one spanning tree. That is the first property. Similarly, all the connected, all the possible spanning trees of a graph, they must have the same number of edges and vertices. For example, you have created 5 spanning trees from a graph. Now, all these spanning trees must have the same number of edges and vertices. Edges mean the links that actually connect the vertices, and vertices also mean the nodes. Another property is that no cycle or loop is allowed inside a spanning tree. And we will see in a moment that we will try to avoid making a cycle or loop inside the spanning tree. Similarly, if you remove one edge, any single edge from the spanning tree, it will make the graph disconnected. The graph is fully connected, but if you remove any one edge from the tree, then the graph will become disconnected. What does it mean? It means that the spanning tree is now minimally connected. Okay? So this is another property, that the spanning tree is formed in such a way that removal of any one edge from the tree will cause the graph to be disconnected. And finally, if you add one extra edge to the spanning tree, what will happen? Actually, it will create a loop, or you can say a circuit or a cycle. And now the the spanning tree will be acyclic. The opposite of cyclic is acyclic. So removal will violate the property of the spanning tree, as well as addition of a new edge will also violate the property of the spanning tree. So in summary, the spanning tree of a graph is actually uh, a connected graph, undirected graph with no cycles and no loops. So it is actually a graph G, which you can represent like vertices and edges. The spanning tree here is a connected subgraph with no cycles, and all the vertices of the tree are covered or connected. Let us see an example, clarify the concept. We have a graph which is mentioned here. and we are trying to identify all the possible spanning trees of this graph. We have four vertices here. The vertices are A, B, C, and D, and they are connected by using different links. And we are going to form the spanning tree for this graph. Yes, we just saw that more than one spanning tree are possible. So how many spanning trees actually do we have here? Total of 16. All these are valid spanning trees. You can see that the number of vertices and number of edges, they are actually the same. Number of vertices are 4. Everywhere, every single spanning tree has 4 vertices. And the edges connecting these nodes is also the same. 3 here, 3 and 3. That is the property of. Now, there is only one half of the story, one side of the picture. The whole exercise is to select an optimal solution from all these possible solutions. We would be interested only in one single solution, and that solution must be optimal, must be the best solution available in all these possible. For that, we have to use another concept that is known as MST, or you can say minimum spanning. Let us see what is a minimum spanning tree. A spanning tree, as we just saw, is a tree that covers all the vertices and that does not contain any side. In other words, you can say that the graph doesn't have any nodes which loop back to itself. Starting and ending points or source and destination are the same. That is not possible. Now, what if we have a weighted graph? A minimum spanning tree is actually a spanning tree that has minimum weight than all other spanning trees of the same graph. Let us take the same example once more. We have we have formed different spanning trees. Now, the minimum spanning tree among these solution will be the one where the minimum weight is possible, like the tree will have minimum possible weight. For example, the overall weight of this spanning tree is 10. Weight could be anything. If you remember the weighted graph, it could be cost, it could be congestion, it could be distance, etc. Here we have 8, here we have 6, and the total weight here is 4. Now you can see what is going to be the best solution in all these cases. The minimum cost, and the minimum cost is 4 here. We will select this spanning tree, and there is the responsibility of the minimum spanning tree algorithm. So you can say that a minimum spanning tree is actually a special kind of tree with some properties, and the properties are like the tree actually minimizes the length, or you can say the weights of the edges of the tree. In real world scenarios, in real world situations, this weight uh, can be measured as a distance, congestion, traffic load, or any arbitrary value denoted to the edge. Take an example. For example, we have a cable company and they want to lay a line to multiple neighborhoods, but they wish to minimize the amount of cable laid, and the company will also want to do it because they will save more money by doing so. Okay, so they have to go for a scheme which will actually lead to the deployment of less amount of cable in order to save more money. And that is the same with the minimum spanning tree concept. We are actually interested in finding a solution that will lead to the minimum cost possible or minimum weight possible in order to to save our resources. And for that, several popular algorithms are available. You can say that different algorithms are available which actually find the minimum distance. And these algorithms include a Kruskal algorithm and Prim algorithm. And that is going to be the topic of discussion. And we will see it in a couple of minutes. What is Kruskal algorithm and what is Prim algorithm? And both these algorithms are used for finding the minimum spanning tree. Let us back to the concept of spanning tree, and let me rewind that a tree that covers all the vertices, okay, and with no loop or with no circuit or with no cycle. But beside from this, in most of the practical application, there is another goal and which needs to be achieved. And the goal is to minimize the total weight of the edges selected if it is a weighted graph. So we can use a greedy algorithms, or you can say a minimum spanning tree to accomplish this goal, this task. Let us see some example to clarify the concept of a minimum spanning tree. The concept can be understood with the help of this example which is mentioned here. We have an initial graph. Here the graph has four vertices A, B, C and D. And every we have associated a number with each edge, or you can say each link. This is actually the weight about which I was talking. It could be anything. It could be distance between the nodes, can be anything. It could be junctions of on a road. Could be two different cities. It could be two computers. They want to communicate. It could be two sensor nodes. Anything. And there is the weight. It could be anything again. It could be distance. It could be the time required to travel to send a packet. It could be anything, any arbitrary number. Okay. Now the possible spanning trees for this graph, not the minimum spanning tree, all the possible spanning trees for this graph, they are mentioned here. So we have four spanning trees. Now what is the total weight, the total cost of each spanning tree? You have to add the number associated with each link. So here the sum is 11. There is 4 plus 5 plus 2. Here the overall weight or sum is 8. 5 plus 2 plus 1. Here we have 8, 10. And then finally we have a sum 7. Okay, very simple. The minimum spanning tree from the above spanning tree is the one with the minimum overall weight or cost, and that is 7. So this is our minimum spanning tree algorithm. Uh, Not algorithm, but solution. Minimum spanning tree, actually. If this example is clear, that's good. If not, let us consider a second example. A minimum spanning tree, sometimes it is also known as minimum cost spanning tree because we are interested in the cost or in the weight. So you can say a minimum cost spanning tree is actually formed from the given spanning trees. Let us consider another example. Here we have different nodes, 5 nodes, A, B, C, D, and E. You can consider them different cities. And then we have different links connecting these cities. And also we have another component parameter, and there is the distance between these cities. For example, if you want to travel from A to A, the distance is 0. But if you want to travel from A to B or from B A, the distance is 13. See, from A to B, the distance is 13. And from the opposite side, from A, sorry, from A to B, and then from B to A is also, here it is, from B to A. The distance is also 13. Because this graph has no directions. It's not a directed graph. So the distance is same from A to B and from B to A. From either side, you will have to travel the same distance. Okay? And similarly, the distance for each and every pair of cities is mentioned in this table. You can also write these numbers on the edges like this. From A to B, we have 13. From A to C, we have 42. From A to D, the distance is 21. And from A to E, it is 14. From E to D, it is 11. From D to C, it is 32. From B to C, it is 20. From B to E, wow. And if I left someone, you can write them as well. Now our task is to find the minimum cost to travel, for example, from A to E. In order to form a spanning tree for this graph, we have to take a source node. For example, our source node is A. And then from here, we have to find the distance to all the adjacent, not all the adjacent, but the more feasible, or the more, the link with less cost. So if you consider from A, you can move to B, you can move to C, you can move to D, and also you can move to E. Let's see here. From A, the cost to B is 13, 42, to D is 21, to E is 14. What is the less cost in this row? That is 13, and it leads to B. So we have selected this arc or this edge. As per the values given in this table, the minimum cost edge is from A to B, or you can say from vertex A to vertex B. And the edge AB is therefore selected in the first iteration, and it is shown in the figure. And these vertices that we have selected would be termed as active. So AB link is now active, or vertex A and vertex B, they are now the active vertices. And this is followed by selecting the minimum cost edge from B to A. Let us see. From B to A we have 13, and others are very much large number. So we have to select it as well. From B to A is also the same. Now the edges that are adjacent to the active vertices A and B, they are AC, AD, BC, DE, and then we have EC and ED. All these vertices or these links are adjacent vertex B and D, which are the active vertex now. But the minimum cost edge among all these unselected edges, there is EC. You can see it from the table that the EC is actually have less cost in all the available options. So we will select this edge that is sorry, not EC. Let us revise the concept. We have the vertices which are actives A and B. Okay, now they are active, and as you can see that the adjacent vertices from A are AC, the cost is 42, AE, the cost is 14, AD, the cost is 21, and similarly to B, there is BE, which is 53, BC, which is 26, and that's it. Among these, the smallest cost is for A to E. As we can see, the cost is 14. So we will select AE as well. Now this is the case. Now we have active vertices A, B, and C. We have to repeat the same process. The edges that are adjacent to the active vertices A, B, and C. We have to identify them. And they are from A, the adjacent are AC and AD. From B, the adjacent are BC, BE. From E, the adjacents are ET and ED. Now you have to find the minimum cost edge among these edges. And after looking at the table, we came to know that the smallest weighted edge is from E to C, having the value 10. So we have to select this. And then now we have to move one step forward. Now the active nodes are A, B, C, and E. And the adjacent edges are, which are not yet selected, they are AC and also AD. From B, we have BC and BE. And similarly from D, we have DC, and from E, we have AD. Okay. And now you have to select the minimum cost among these unselected edges. After looking at the table, we came to know that the smallest one among them is from E to D, and that is 11. So we have selected it. Now that's it. Since all the vertices, if you see here, have been covered, the task is now accomplished. Okay? You see all the vertices, all the nodes are now connected, and there is no loop. Okay? There is no loop. One consideration is that the number of edges in a spanning tree of a graph having n vertices, it should be n minus 1. So we can see here from this graph that now we have 1, 2, 3, 4. We have 4 vertices. Sorry, 4 edges. And 4 is actually, if you calculate the number of vertices, there is 5. So 5 minus 1 mean n minus 1 equal to 4. There is the formula. It fits. Okay. So this approach qualifies to be a greedy approach. Remember, we are studying approaches which actually follows the greedy optimization problem. And this is actually a greedy approach. Why? Because the decision is taken by considering the path which is the most promising at that particular time. We are only looking at the next level, the next solution, which is best at that time, at that particular time, at that point of time. Okay, so this is actually a greedy approach, and this is best for many scenarios. Now let us see how we can actually find this MST for a graph by using different standardized algorithms. We will focusing on two solutions. The first one of that is known as Kruskal algorithm. Let us see what is Kruskal algorithm. The Kruskal algorithm finds out the minimum cost spanning tree or minimum spanning tree or MST by including the minimum cost edge or the minimum cost link in each step of the solution, and we have to put it into the output tree. The condition remain is the same. You have to proceed in such a way that you will have to avoid the cycle. Cycle should not be performed. Okay? So Kruskal algorithm is actually a minimum spanning tree algorithm that takes a graph as an input. Remember, we have to provide an input, and the input is a graph. Then after providing the input, this algorithm will find the subset of the edges of the graph, which actually forms a tree, and the objective is that the resultant graph must have minimum sum of weights among all the possible solutions. Some of the things that I have highlighted here, they are important to remember. First thing is that in the Kruskal algorithm, we have to give attention to the edges. To be more specific, we need to give attention to the cost of each edge or to the weight of each edge or each link. That is important. Second thing is that we have to proceed towards the final solution, but we need to avoid cycles. For example, if you are moving from A to D and there is a cycle in between before reaching to D, then you have to avoid that path. We have to avoid the cycles, we have to avoid the loops, we have to avoid the circuits. Okay? And finally, the algorithm actually identify the, the solution which will have the minimum sum of bets, mean the optimal solution, as we just saw here in this case. Okay, so these are the objectives of the Kruskal algorithm. Now let us see how it actually works. Let me repeat that this algorithm, Kruskal, actually falls under a class of algorithm which is known as greedy algorithm or greedy approach, and that find the optimal solution at a particular instance of time, with the hope that at the end we will have a solution that is going to be global. Like for example, if something is good for this particular case, at the end we will get a solution that will be optimal for the global problem. Solution is going to be optimal for every for the big problem as well. Okay, so we start from the edges. Remember, again, we start from the edges, and then first we have to sort the edges in ascending order from low weight to high weight. Okay, let me tell you one thing. These steps are only for implementation of this algorithm, but our concentration in this course is not on the implementation. Okay, so we will not go into the further details of the implementation concepts. Rather, we will focus on the algorithm, its operation, or how it works by taking some examples. But still, you need to know that if you want to implement this algorithm, the criteria is that you have to sort the edges in ascending order from low to high weights. After that, in the second step, you will have to take the edges that has the lowest weight and you will add it to the spanning tree or the output. But remember, if that solution lead to a cycle, then you have to reject it. You will not include it into the output. Okay, because we will try to avoid cycles, the loops. And then you have to continue repeating the step, adding the edges until we have covered all the vertices, until the graph is connected, fully connected, all the vertices are accessible. If we reach this condition, then it's time to stop. This is how we can actually implement the Kruskal algorithm. Now let us see how it actually works with the help of an example. Example number 1 actually is about Kruskal algorithm and how it works. The graph which is mentioned here is actually a weighted graph. Okay? We require a weighted graph in order to decide which solution is optimal. And also the graph has no directions, undirected graph. Step number 1 of the Kruskal algorithm is, let me stress here again. We have to stress the edges here. Later on, I will compare Kruskal algorithm with the Prim algorithm. So there, it is important to note that here we are actually focusing, concentrating on the edges. So we have to start from the edge, which has the least weight You can see every edge has a cost associated with it. What is the lowest number here? What is the lowest cost here? What is the lowest weight here? That is 2. But wait a minute. We have two edges with the same weight. Now what to do? Which one to select? Okay, that is understood that we have to select an edge with the least weight. But if there are more than one edges with the same weight, then what to do? Which one to choose? Option is your choice is your. You can choose any one of it. You can choose this one. Sorry, the nodes are not labeled, so it will be a bit difficult to name it properly. But let us say A, and this is node B, and this is node C. So you can either select A to B or you can select B to C because the weight of these two edges is the same. You can select either one. We are going to select this edge. Now, after selecting this one, the next step is to choose the next shortest edge and add it to the output. Our output for the time being. So the next one is this one. Is 2. Add it to the output. That's it. Now we have selected these 3 vertices and 2 edges. What next? Repeat the same. Choose the next shortest edge. It doesn't create a cycle, remember the condition. And then we have to add it here. So the next possible edges are this one. Let's suppose this and this B. Which one we have to choose? Either C to D or B to E, because both have the same weight. Let's suppose I have choose this one. Now equation is like this. It has been selected as well. So the graph is like this. Again, choose the next shortest edge that does not create a cycle and add it to the output. Let us see what is going to be the next one. Okay, here you can actually watch that we have again 2 edges with the same number 3. So let us this one bring the weight 3 and add it to the output 3. Here they have selected this one. So the situation is going to be like this: already selected. Now we have to select either this or this, so they have selected this one, already selected, and the situation is like this. Now again repeat the same process. What we need to do now, we have to select either this one or this one, but we cannot select this. Why? Because it will create a cycle and we have to avoid the cycle. What next? Ignore this one, although it is less, although it is the minimum value available at the moment, but we have to choose 4. So the next step is like this. Select this, it will create a cycle. Now at the end you will see that we are done. All the vertices are now connected and we do not have any cycle here. And this is how we use Kruskal algorithm find the MST. And this is actually a minimum spanning tree because it has the minimum cost. And this is actually a greedy approach because we select the solution which is best at that particular instance of time. And we assure that the global solution, the overall solution, is also the optimal. But that is not true in all the cases. But majority of the time we will get a globally optimal solution as well as the result of Kruskal. Let us consider another example of the Kruskal algorithm. Here we have to use the same algorithm the Kruskal algorithm for the graph which is given here. Now we have the vertices numbered from A F, and again they are connected by links, and the links, every link has a number, has a weight associated with it, which actually represent the cost or weight or value, which is an arbitrary number. First thing first, remember we have to focus on the edges. We have to start from the edge which has the lowest value in this graph. Let us see, let us find. Okay, we got one. The minimum cost is from B to C. Since B to C is the least cost edge, then B to C will be selected. The dark line means that B to C has been selected in the first iteration of the Kruskal algorithm. What next? Now from amongst the remaining edges which are not dark, okay, we have to select the least cost edge. Let us see. But they must be reachable from the active nodes. E to A10, E to A8, E to E7, B to D4. I think the least cost is, and that is B to D. So make it dark, B to D. Now the active nodes are B, E. Now from amongst the leftover edges, we have to find the one which is the least, which has the least cost. So if you pay attention, the cost here is 7. Here we have 8, 5, 4 is already been selected, 10 and 8. I think the least cost is 5, and that has been selected and put into the output file. Repeat the same process. Find the minimum cost. As you can see, the minimum cost is 7, but we cannot do that. We cannot select CE edge. Why? If you do this, it will become a cycle. See, this is a cycle, and we have to avoid the cycles, so we cannot do it. We have to search for something else, a number that is greater than 7. So the edges, if you pay attention, here we have 8, here we have 8. From A to C or C to A, and from a D to F or F to E, we have the equal weight, that is 8. So you can select any one of them. Let's suppose we have selected A to C. That's it. In the next iteration, we will select D to F, and that's it. After this, you would see that now all the vertices are connected. For example, I want to travel from A to F. Is it possible? Yes. Go to C, then to B, then to D, to F. That's it. And the cost, you have to add all the cost of the individual edges to get the overall sum graph. This is actually a minimum spanning tree, which is a greedy approach, and we find this minimum spanning tree by using the Kruskal algorithm. Finally, let us see a third example. I would rather say that you could try this example by yourself. Only 2 steps are mentioned here. Okay. First, you have to give concentration to the edge, the numbers associated with each edge. The lowest number is 1. So mark these edge as red. Now these 2 nodes or vertices are now active. See the neighbors, see the directly connected neighbors. To B, the cost is 5. To D, the cost is 4. To D, the cost is 3. And to E, the cost is 2. I think this is going to be the next choice because there is now the minimum value edge in the remaining. And then you can proceed with the rest of the graph. Finally, you will get something like this. There is the minimum spanning tree. The edges that are highlighted by the red, they are actually considered, and the edges they are not highlighted, they are not considered, they are actually ignored. Now we have a fully connected graph, undirected graph, and the edges selected are actually the minimum cost available at that particular time, and this is a greedy approach. Okay guys, before moving to the next algorithm, I would like to show an animation. Please give me time. Okay guys, here we do have an animation of the Kruskal algorithm. This is something related with the implementation, but we will not go into the details of the implementation because they have used the concept of disjoint sets here in order to facilitate the implementation. We will focus on how actually the Kruskal algorithm technique work. Let us start. We have a graph given, and these remember for the implementation you have to write the edges along with their values, their cost, their weights mentioned here. For example, A to C we have 7, A to E we have 9, and other as well. And here we have the disjoint cells, the disjoint set. Okay, this is actually the tree. We have all the nodes mentioned here. This is actually an array starting index is starting from 0, but we will not go into the details of here. Let us focus on the Kruskal algorithm itself. Let us start. Okay, processing edge EF. Why? Because there is the least value. The least value of the edge is from E to F. So we have selected this edge. Let us move one step forward. Okay, here is something related with the implementation. Both the nodes are considered. That are E and F. E has no, the parent of E is actually E. This is not a parent X, okay? The parent of E is E and the parent of F is also F. So we need them to build a relationship, and there is going to be like a union of the nodes. Now E to F we have a path, and the cost here is 1. We have to concentrate here. We have identified the edge with the least value, that is from E to F, and we have give it the red color, which mean okay, now this has been part of our solution. If you want to travel from E to F, that is the best route. Next one, identify the second path between two vertices with the minimum cost or value or weight. Here we have 9, here we have 7, we have 5, we have 2, and we have 2. Oh, 2 paths with the same value. Up to you. The one which either one you will select is, we have selected C to D. Sorry. We have another value that is 1, that is less. Okay, so we select it from C to D. Now see the parent of C itself, and the parent of D is D itself. So we have to reunion them. D will now be the child of C. That's it. But we are not interested in this. We are interested here. We have identified the next edge with minimum value, and that is C and D. So it will be highlighted. That is part of this now. Next, find the next edge with the minimum value, that is either C to F or D to F, or you can say F to C or F to D. Up to you. Either one you can select. We have selected from D. I've selected from D to F. This one. Okay. Now see, D has a parent that is C, and also F has a parent that is E. So what does it mean? Means that have to union them like this, because the parent, if you see, the parent of D is C and the parent of F is E. So we can reunion them like this. Now the parent of D and E is, but here we have to color them red like this, and this is now our path from D to F, and this is part of the output. Next, this is important now. Look, the minimum value is 2, and the edge is from C to F. Now see, what is the parent of C? Is the parent of C itself. Now what is the parent of F? The parent of F is C as well. What does it mean? If they have the same parent, it means they are already unioned. Okay, So we cannot reunion them. And if now you see here, that is not possible from C to F. Why? Because if you make it part of the output, part of the solution, then it will become a loop. See? And that is not possible. We have to avoid the loops. And you can see from here as well. That is not possible. We will not make it part of the solution. We will ignore this edge, although it has the lowest value now, but we will ignore it. Okay. Next, find the edge with the minimum number, and that is 5. The nodes are C to B. Let us see here. The parent of C is C itself. Okay, but the parent of B is B itself. So C will become the child, sorry, B will become the child of C now. Okay, for our interest, concentration should be here on the graph. C to B, the cost is 5, and it does not lead to any cycle. So we will identify it and will make it part of the solution. Next, find the edge with minimum cost. It's 7, 9, and 6. Oh, this has the minimum cost, so we will have to make it as part of the solution. Not part of the solution, but we have to consider it. Let us see. Parent of C itself. Sorry, parent of not C. Parent of F is, you can see from here, parent of F. Parent of B is always C, also C. Means they are already in union. So you cannot reunion them. Or if you see here, B and F, you cannot join them. You cannot consider it to be part of the solution. Why? Because if you did it, this line will become red, which means cycle. And we have to avoid the cycle. So ignore it. Move forward. Identify the next edge with the minimum value. That is C to A. See? To A, that is 7. Okay. I will go for fast now. We will make it part of the solution. That's it. Next, we left with A to E, but we cannot do it because it will become a cycle. That's it. So this is the minimum spanning tree using Kruskal algorithm. This was an animation, you can try it as well. Back to the lecture. Our second algorithm is known as Prim algorithm. It is also a method by using which we can find an MST or minimum spanning tree. Actually, the Prim algorithm is simpler as compared to the Kruskal algorithm. And the Prim algorithm is a minimum spanning tree algorithm that takes a graph as an input. Remember, in both the cases, we have to take a graph as an input. And then we have to find the subset of the edges for that graph, which will actually form a tree that include every vertex. Every vertex will have a minimum sum of weights among all the tree, and also there will be no cycle. So the first step of this algorithm is to find out the minimum cost edge from the source node. Okay, one thing I would like to say is that in Prim algorithm, we have to focus the node. Remember, in the Kruskal algorithm, we were focusing on the edges, the minimum edge. But here we have to focus on the initial node. What is going to be the initial node to start our algorithm, the operation of our algorithm? So the first step of the algorithm is to find out the minimum cost edge from the source node. Node. You do not have to pay attention to the edges. In the first step, you have to select any source node and then find the minimum cost edge from that source node. So in summary, you have to give attention to what is going to be the starting node for the algorithm to operate. And then this is followed by adding by addition of the minimum cost edges. Obviously, we have to do that in a way that no cycles are formed. Now, how this algorithm works? This is something again related with the implementation, but for understanding, let us see how it works. Actually, this algorithm, as I just mentioned, also fall under the category of the greedy algorithms because it take a decision in local circumstances, what is the best solution, what is the optimal solution at that particular instance of time, and then we hope to find a global optimum solution, as we saw in the case of Kruskal algorithm. But here we have to start from one vertex, as I just mentioned, not from the edge, but from the vertex. And there is the main difference between the Kruskal and Prim algorithm. There we start from the edges. Here we start from the vertex or node. And then it is followed by adding the edges with the lowest weight until we reach our goals. So the steps in summary are as follow. You have to initialize the minimum spanning tree with a vertex of your choice, and you can choose it at random. After that, you have to find all the edges that connect the tree to new vertices, but the condition is that minimum value, and then you have to add it to the output tree or graph, and then you have to repeat this step again and again until we get the required minimum tree. Let us see an example. Similar example, but we are going to apply a different algorithm, and that is the Prim algorithm. What's going here? The first step is to choose vertex randomly. Suppose we have, this is given to us, this graph. If a question come in the examination, the graph will be given. The weights should be here, or maybe the weights are given in a table. Okay, then you can put the weights on edges. The first step is to choose any node, randomly selected node. Let's suppose the node that we have selected is this one, node A. Sorry, the nodes have numbered. The cost from A to B is, okay, next thing is simple. Choose the nearest vertex from here or here, from A or, but the vertex should be the one that is not actually part of the solution or that has not been selected. So if you see the edge with the minimum number is this one. Let's suppose this is, so we have to make it part of, solution. And then from that particular node, choose the nearest edge not yet included in the solution. And if there are multiple choices available, choose one at random at your own choice. So if you see from here, we have three. I have selected this one to be part of this, and that is mentioned over here. Next, you give attention. The minimum value is here, 3. That is make part here. And after that, it has been done directly. The next one is with the weight 4. That is here. So this is actually make part of solution. And then we will get a spanning tree like this. Let us see the second example. The second example is almost the same as we saw in the case of Kruskal algorithm. Uh, but here we have to start from any vertex, from any node, not the edge. Suppose we start from A. This is our starting. We have selected A to be the starting vertex. Now, since from amongst all the edges that leave the node A, for example, A to C and A to B, the smallest edge value, or the edge with the smallest value, is AC, because the value here is 1. That is the least cost. So AC has been selected, and you can see it here. The dark lines show that we have selected AC, and it is now part of the solution. In the next iteration of this Prim algorithm, now you have to select the edge which has the least cost. The active nodes now are A and C. The edge from A to B has a cost of 8. The edge from C to B has a cost of 5. And the edge from C to B has a cost of 7. What is the smallest value between 3? 5. So we have selected this one. Now the active are A, B. As you can see, the smallest now is 2. You have to select this one. Now the smallest here is 2. So DE has been selected. Next, the smallest value is from D to F. So this one has been selected. Okay, I think we are done. Oops. Because all the vertices are now connected and we do not have any cycle there. Let us see animation of the Prim. Here we have animation. As I just mentioned, Prim is simple to code, simple to implement, and here you can see we can implement it in by using a simple array or simple array of vertices. Let us see. We have a graph given. The first step to do is to select any arbitrary node randomly. Suppose we have selected A. Okay. Now you have to select the edge from A which has the lowest value. So from A to E the cost is 9, but from A to C the cost is 7. Obviously we have to select the C. The next vertex is C and the cost is 7. Okay, so make it part of the solution. Now the active vertices are A and C. The cost is 9 here. Here the cost is 1. That is obviously the lowest, the least cost. So make a C to D the edge part of the solution. So D is selected now. The cost is 1. Make it part of the solution. Give it dark color, red dark color. That's it. Now we have three active nodes. Let us see the cost. The cost from A to E is 9. From C to D is from C to B is 5. From C to F2, from D to F2. Both have equal chances of selection. You can either select C to F or D to F. Let's suppose we have selected D to F. So the cost F is, and the link, sorry, they have selected C to F, not, doesn't matter. So C to F the cost is 2, and that's it. Next, you have to find the edge that has not been selected yet and that has the lowest or least cost. From A to E, the cost is 9. C to B, the cost is 5. F to the cost is 6. F to E, the cost is 1. That is the choice. F to E, 1. Select it. Next, one step forward. Okay. You now you have different options from A to B. That is not possible. Why? Because the cost is very high, and also if we make it choice, then it will lead to cycle. Next, we have two options: C to B and F to B. The least cost is from C to B, so there is going to be the choice, and that's it. We have covered all the vertices, and the resultant minimum spanning tree is like this. The directions. Okay, guys, this was about greedy approach, uh, optimization problems, Kruskal and Prim algorithms, things like that. Let me conclude today's lecture. Okay, so in today's lecture, we studied about the greedy approach and about the minimum spanning tree, Kruskal and Prim algorithm. In summary, let me conclude like this. If you have given a connected and undirected graph like this is actually a connected undirected graph. A spanning tree of this graph is actually a subgraph, not a tree, you can say, which actually connects all the vertices together. Connected graph, and there will be no cycle. An edge starting from the node and ending at the same node. That is like a cycle, or you can say circuit, a loop. Second important point, that a single graph can have many different spanning trees. Now we are interested only in one solution. So the minimum spanning tree or minimum cost spanning tree or minimum weight spanning tree for this graph is actually a solution that also lead to a graph which is connected, fully connected, and the graph is also undirected. but it will have the least weight. For example, if you have 10 spanning trees for a graph, so what is going to be the minimum spanning tree amongst them? The one which lead to the least weight among them. So the weight of a spanning tree, as you know, is actually the sum of the weights given to each edge of the spanning tree. You add all the cost, all the weights of the individual edges, and then you get a sum of the weights. That sum must be less from all the sums of the other spanning minimum spanning tree from the other spanning trees. Sorry, used. Okay, let me revise. If you have a graph like this, then several spanning trees are possible. But we are interested only in a particular spanning tree. What is that tree? That tree is known as minimum spanning tree, or minimum cost spanning tree, or minimum weight spanning tree. That is actually a tree, a graph that is weighted, connected, and undirected without any cycle, and the total weight of that spanning tree should be less than the weight of all other spanning. In order to find a minimum spanning tree, we can actually use different, like Prim, like Kruskal. They are famous algorithms that actually uses the greedy approach, or you can say optimization. They work towards optimization. Both the Prim and Kruskal algorithm are greedy algorithm, and they are used for finding the minimum spanning tree. Remember, both the Prim and Kruskal algorithm are actually greedy algorithms, and they are used for finding the minimum spanning tree. But you can apply these algorithms on graphs that are weighted, that are connected, and that are undirected. Finally, there is a difference between the Kruskal and Prim algorithm. The main idea behind the Kruskal algorithm is to sort the edges based on their weights. Remember, we focus on the edges, and then from implementation point of view, first we need to sort the edges in ascending order from low to high. After that, we start taking edges one by one based on the lower or least weight. In case we take an edge and it result in forming a cycle, then what we need to do? This edge is not included in the resultant MST. Okay? We ignore it. But if it does not lead to a cycle, then we include it in the result MST. On the other hand, the Prim algorithm is actually a modified version of the Dijkstra algorithm, shortest path finding algorithm. Here in Prim algorithm, we first choose a node, not an edge. We randomly choose a node to start the algorithm. And then from there, we add all its neighbor to the output solution. We perform multiple steps, and in each step, we extract the node that we are able to reach using the edge with the lowest or least weight. And therefore, you can say that we extract the node, we add them to the resultant minimum spanning tree if it does not lead to a cycle, as it's in case with the Kruskal algorithm. So, in conclusion, the main difference between these two algorithms is that in the Kruskal algorithm, we start from the edge, while in the Prim algorithm, we select any node or any vertex randomly, then we decide. Other differences are also there. Uh, for example, if all the edges weights are, this is a bit technical, but let me share with you that if all the edges have the same weight, not the same but distinct weight, the weights of all the edges are unique, there is no duplication in the weight, then both the algorithms guaranteed to find the same minimum spanning tree. they will lead to the same solution. You can say if the weights are distinct for the each edge. But if the edges are weight associated with the edges, if they are not unique, they are not distinct, then both the algorithm may not always produce the same MST. However, in both the cases, uh, both the MSTs produces by these two algorithms would would always be the same if the weights are distinct. Let me revise it. If the weights of the edges are unique, then both the algorithm will find the same minimum spanning tree. But if the weights are not distinct, there are duplication, then the algorithm may not always produce the same MST. Another thing about Prim algorithm is that it actually initialize with a node, while Kruskal algorithm initiate itself with an edge, as we just. Okay, from implementation point of view or from the usage point of view, Prim algorithm is preferred when the graph is dense. On the other hand, the Kruskal algorithm is preferred when the graph is like a sparse, with no many edges or nodes. And finally, there are some other solutions. There are also some other differences between the two algorithms. Maybe if you are interested, you can find on the Google about these two algorithms, about their comparisons. For example, the Prim algorithm, it grows a solution from a random vertex. Select any one randomly, and then adding the next cheapest vertex to the existing solution. While the Kruskal algorithm grows a solution from the cheapest edge, the edge with the least cost, and then we add other edges to the solution. Okay, other differences are also possible between these two. For example, the Prim algorithms always gives connected component, while the Kruskal algorithm can generate forest which may contain disconnected components and things like that. So if you are interested in more differences, you can see some information on the Google about these two algorithms. This was about today's lecture. uh, I hope you have learned something lecture with another lecture. Then goodbye.